All right. Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, August 27, 2021. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a hot and humid summer evening in Rockport, Massachusetts. These Earth and Space Reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about the life-sustaining environment of our home planet, and who wonder about the greater cosmos, including our place in space and moment in time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. Today, we are joined by members of the Rockport Research Explorers, Rockport Cultural Council, Gloucester Area Astronomy Club, far-flung friends and family, and other curious folk. Thank you for coming. Our special guest for this evening is Dr. Shadia Habbal. Shadia is an astronomer and faculty chair at the University of Hawaii's Institute for Astronomy. She is originally from Syria, where she earned her bachelor's degree at the University of Damascus and her master's degree at the American University of Beirut in Lebanon. She then moved to the States, where she earned another master's degree and a doctoral degree at the University of Cincinnati. I had the pleasure of overlapping with her several decades ago when we both were working at the Harvard-Smithsonian Center for Astrophysics. Since then, she has been very busy studying the origin and evolution of the solar wind, the stream of charged particles that flows outwards from the sun. She also studies the enigmatic solar magnetic field, which seems to be responsible for many things, including extremely high energy phenomena such as solar flares. She receives major research grants from the National Science Foundation and NASA to pursue the study of the solar corona, which can only be seen from Earth during a total solar eclipse. She currently serves as principal investigator of her research group called the Solar Wind Sherpas. This evening, Shadia will talk about the scientific magic of total solar eclipses. So welcome, Shadia. I'm delighted that you could come and share with us your fascinating research.
Thank you, Bill, very much for the invitation. I guess, can I start sharing my screen?
Yep, this is the perfect time.
Okay. So good morning, good evening, good afternoon for all of you, depending on your time zone. It's really an honor and a pleasure for me to be talking to you. And I'm so glad that Bill actually, contacted me. So what I'd like to share with you today is the research that is taking up more than half of my time. And this is to observe the solar corona during total solar eclipses. Now, these are unique events that will enable us to observe and to study the most interesting part of the corona, which basically starts from the solar surface and expands out to a few solar radii. So I know most of you are scientists, but I just thought I'll go over, or with scientific background, or just to remind you how a total solar eclipse occurs. So it's this very fortuitous alignment between the sun, the moon, and the earth, when the moon can totally block the disk of the sun. And this is the only time when you can actually see the corona. Otherwise, you have partial eclipses, which are also precursors to before you get a total solar eclipse. Now, unfortunately, this condition only lasts, or this alignments last for only a few seconds to a few minutes, but despite this paucity and their occurrence every 1 to 1.5 years, it's still an incredible opportunity to explore this expanding atmosphere of the sun with all its impact into the solar system and on all the objects in the solar system, most notably our Earth. So I won't go through this. This is from Michael Seiler's website, and it just gives you an idea of the total solar eclipses over North America that will happen in the 21st century. So I won't be there, I'm sure, for most of them, but it's for future generations, it's quite impressive. Now, this is just focusing on North America, but the same applies to, if you take the whole map of the world, The eclipses happen, their shadow band covers different parts of the world. But interestingly, about 70% of the eclipses occurs over the ocean. So before going into the science, I'd like to just go back a little bit in time to account for the first really critical observations that were made during total solar eclipses. So this is just going back to historical records about 1300 BC and 1200 BC. So although this says, this is an example of a tablet from China, it's not the one which had an inscription that says 3 flames ate up the sun and a great star was visible. So the conditions during a total solar eclipse is such that it's almost like nighttime and you can see stars, which is quite remarkable to happen during the daytime. One of the oldest records of a verifiable solar eclipse was discovered on a clay tablet in Ugarit in northern Syria. Now, before the advent of photography, people, of course, this was a phenomenon that caused a lot of awe and sometimes fear among those who witnessed it. But those who were interested enough with a scientific mind, they made sketches of what they saw in the sky during a total solar eclipse. And these sketches were quite remarkable. And my understanding is that with many expeditions, there was a large group of mostly women who were asked to come along to make these drawings. So you can see in the left example from 1878, the exquisite details of what was by the observer who captured it. And in particular, these red features here, which we call prominences. This is only a few years, well, a decade later, with the beginning of photography. You can see this is a large glass plate, but you can see that the limitations of photography, although it's a recording of the state of the corona, you have the problem of having to contend with exposure times, which your eye manages to overcome. And so if you take a long exposure, you saturate the inner corona and then you see the outer corona. So what subsequently nowadays, what we do is we take a sequence of observing exposure times, and then we put them together with some image processing techniques. But this is just to give you an idea of how things, advanced. So it's going back almost 150 years. Now, one of the major discoveries, and people underestimate the importance of this discovery, was made in 1869. So this was when the spectrometer was invented and people could actually try to analyze the light that was coming from the corona. And they discovered that actually you had the colors, basically the colors of the rainbow. And in 1869, what they discovered was, so this was a slitless spectrometer. So you see here in green was emission from a line that they couldn't identify with any emission from something known in the lab or on Earth at that time. So this was in 1869. And it took, it wasn't until 1941 that Edlin and Grotrian identified it as what we call iron 13 plus, or also the astronomer referred to it as iron Roman numeral 14. So it's an iron that has been stripped of 13 electrons. And for this to happen, the temperature of the gas has to be at least 2 million degrees. So you can imagine the impact of this discovery, because this was the first time that people realized that the atmosphere of the sun was far hotter than the photosphere, the surface, at about 6,000 degrees. And that for this temperature, most of the elements, I mean, almost all of them, should be fully ionized. This discovery led Gene Parker to show that the corona couldn't remain bound to the sun, and it had to expand supersonically in what he he called this expansion the solar wind. Now, in 1963, the existence of the solar wind was confirmed by in situ spacecraft that were orbiting orbiting in the ecliptic plane. And the first one, I'll show you an example here, but I just wanted to also mention the implication of this finding is that then it was realized that the corona could be observed in X-rays and ultraviolet without having to rely on total solar eclipses. So this is the confirmation from the Mariner 1 spacecraft in 1963 that went out to the orbit of Mercury, and it was well outside the magnetosphere of the Earth. And this is the plot they have in the, I forgot to mention the reference, but it was from Neugebauer and Snyder. It was a very simple detector. So it measured the density of the particles and the speed. So the darker curve here is showing you the speed, and the lighter one is the density. So this was taken over about 3 months from August to December. There were some data gaps here, but these first observations demonstrated that there was a solar wind, that the speed varied anywhere from 300 to 800 kilometers per second, and that the density and the velocity were varied they were opposite of each other. So whenever the density was high, the speed was low, and whenever the speed was high, the density was low. So this was the beginning of the realization that you didn't just have a solar wind, a continuous flow, but you also had quite a bit of variability. And with all the subsequent spacecraft, this first observation, it has been confirmed all the time. Now, the evidence for the expansion of the corona also exists in the ionized tails of comets and also in the aurora borealis. So this is the penetration of mostly solar wind electrons into the upper Earth's atmosphere and ionizing the oxygen and the nitrogen, producing these beautiful lights. So as I mentioned, the realization that the corona was so hot led to the first rocket flights with payloads that had X-ray imagers and EUV imagers to look at the sun. And that confirmed that you could actually look directly at the surface of the sun, because you're looking at the corona, and the photosphere is basically doesn't emit in the EUV, so you can observe the solar corona. So one would ask, well, why do we still need total solar eclipse observations if you can go to space and observe the sun continuously and observe also the solar disk, not just when it's obstructed? So what I'd like to show in what follows is really the remaining or the still unique advantages of total solar eclipses. So this is an example. The picture here is from the Solar Dynamic Observatory. It's a combination of 3 different wavelengths, just to show you how you can see the solar disk in the EUV and in the small section of the corona above the limb. Now, because of the excitation properties of the spectral lines that emit in the EUV, the extent of the emission is rather limited. So this is just to, and the other breakthrough in exploration of the corona came with the design and invention of the coronagraph by Bernard Liot, who was a very avid eclipse chaser, but he wanted to observe the corona not just during eclipses, and he came up with this design of placing a man-made occulter in the optical path of your telescope so that you can obscure the moon and then see the corona. Now, this is from the LASCO C2 coronagraph on SOHO, which is still operational. So you can see what's missing here is this the gap between what you see in the EUV and what you can see in the LASCO. So all you see is, okay, so it's extremely complex on the surface, but then here everything goes out almost rather simply. You can see the expansion of the corona. You can see how you have different density structures, etc. Now, mind you, these two observations were taken on the same day. And here I'm overlying it with the eclipse image from the same day. So you can see that without the eclipse image, you really wouldn't have been able to guess how the inner corona that's observed in the EUV is connected to the outer corona. And this remains still the case. So the other curious thing that was also discovered during a total solar eclipse was in 1860, when Temple made this very interesting drawing. And there was this feature here that some people thought, well, maybe it's an observational fluke or whatever, but it was very strange looking. And nowadays we know, and it was with the beginning with Skylab and a few rocket flights before using a coronagraph, that solar physicists discover these coronal mass ejections. They're very faint bubbles that expand through the corona at different speeds depending on the conditions. And they actually have a tremendous impact. They can have a tremendous impact on the Earth's magnetic environment if they are Earthbound. So these are now examples from the LASCO C2 of how you see the coronal mass ejections expanding through the corona and going out as a bubble. So these are two different processing techniques. I'm showing the same thing. This shows you the occulted sun, and here you have the coronagraph occulter, and so this is just showing the difference, and this is just flattened. So this is just an illustration. The example from 2013, there was a total solar eclipse during solar maximum, and these two are taken at exactly the time of the eclipse. Now, the eclipse image captured several incredible features. This one was a prominence that erupted, and I'll talk a little bit more about it. This was followed the passage of a coronal mass ejection through the corona. And this one was what we would call a perfect classic or textbook coronal mass ejection, which is in the shape of a light bulb with the filament at the center. So here what I'd like to do is just to run, since the LASCO observations were taken all the time, so we have observations prior to the eclipse. And then you will see how this feature expanded from behind the occulter. And this is what I want to emphasize, that we missed all the beginning. And you start to see the precursor to this filament that's coming out here. And then at exactly this time, you catch exactly what's seen in the eclipse image. So this is just to show you how incredibly detailed the eclipse images are. They have a much higher spatial resolution, and you can tell where they started at the sun and expanded outwards. And in this case, the prominence ejecta, which people call the filament or the core of the CME, remain tethered to the sun. This is just a model animation to show you what the impact, if you have a coronal mass ejection, how it's impacting how it can impact the Earth's magnetic environment and change the whole pressure in the magnetosphere and cause the aurorae display in the north or southern poles, close to the pole. Okay, so now what is driving the complexity of the corona, and why is it changing over time? So these are two pictures of the sun that you can observe on a regular basis if you have the right protection to either your optics or to your eyes. This one was taken in 2001 when at solar maximum, when you had several sunspots, and this is in 2018 when there was only one or two here. And Bill was saying that today he saw there were 3 reported on the sun. But the point is, okay, we know, perhaps you all know this, that these sunspots are due to high concentrations of magnetic field that was discovered by Hale in 1905. And that there are very long records, time-wise, records of the number of sunspots, and the number changes. It has a cyclical variation, which we call the sunspot cycle, which varies anywhere from around between 10 and 12 years. It goes to like a maximum number and a minimum number. And this maximum also varies as a function of time. And this is a period where there was a minimum in solar activity. And I won't go into the Maunder minimum because I'd like to mostly focus on the eclipse data. This is an example. So how does this magnetism or these magnetic manifestations on the solar surface translate into what we see in the corona? This is a compilation from our eclipse observations from 2001 to 2019. The images were processed by Professor Druckmüller in the Czech Republic. And you can see the incredible intricacy of the structures in the corona that vary as a function of time. So this is at solar maximum. You go to minimum when you have these, what we call streamers that are kind of more limited to the ecliptic plane. And then you go back through maximum. This cycle had almost 2 maxima in 2012 and 2013. And now we're past the solar minimum, but I'll show you some pictures from the 2019 eclipse. So clearly there is a connectivity between what we see on the surface as far as magnetism and its manifestation in the corona. So now I'd like to go on to talk about the colors of the solar corona. If you remember the spectrum I showed you from 1869 and excuse me. So the sun, if you look at the photosphere and you take a spectrum, this is a spectrum that has been taken from Kitt Peak. Excuse me. It goes because it should be all lengthwise. You can imagine you go from the blue to the red, but you're going you're starting every row with a continuation of the previous one. But the point is, it's an incredibly rich spectrum, and you also see the absorption lines. So all these elements will have manifestations in the corona. Excuse me. Okay. So it just so happens, and by fortuitous luck for scientists, that iron is one of the dominant elements in the corona and in the solar wind. And it has been observed at different ionization states. So it emits in different ionization states in the corona. So these are the lines. As I said, iron Roman numeral 9 means that it's like iron 8+. So to get to these lines, you need different electron temperatures. So by observing these different lines, you can actually probe the electron temperature in the corona. So you start with iron 9, which is, well, you have others, but this is the temperature which is likely to appear in the corona. And this one goes all the way to iron 14. So you have the beauty of these lines is their peak ionization temperatures are well distinct. So if you, for example, see something in iron 13 here, okay, part of it might overlap with iron 14. And I'll show you examples where you can clearly see distinct structures, even in lines that have close enough peak ionization temperatures. So this is an example from 2019. As I said, it was, we observed it from Argentina, and it was close to solar, almost at solar minimum. This picture was taken by Peter Annual and Miloslav Druckmüller from Chile, and we were in, so the team was split into 3 observing sites, and I'll talk about it later, and we were in Argentina. So these are the observations that were taken. So what we do to observe in these different spectral lines is we retrofit our optics with what we call a narrow bandpass filter So basically, you're observing, you're extracting from all the spectrum of the corona. You're just taking 5 angstroms worth of light, which is centered at different wavelengths. So this one is centered on iron 10, which is formed at close to 1,000,000 degrees, iron 11 at 1.2 million, iron 13, 1.6, and iron 14 at 1.8. So just looking at these pictures, you can already see the difference in the corona as you look in different spectral lines, which is a reflection of the electron temperature distribution in the corona. So we know from white light that it's such a finely structured atmosphere. And here from these observations, we see how it's almost every fine structure has a different temperature. So if by just overlapping these with different color schemes, it's another way of showing how, for example, in this example, iron 10 and iron 11 are have a very close peak ionization temperature, but it's clear that even with this small distinction, you have different features appearing in the corona. So this is all addressing a big puzzle that we still do not know. How does the sun produce such a hot atmosphere when its surface is at only 6,000 degrees? Now, not only is it a hot atmosphere, but you have a very finely structured atmosphere structured by the magnetic field. But it's also, there's a heating mechanism or processes that are also leading to distinct temperatures in different structures. Now, I'd like to, this example is from 2008, and it's probably one of the most beautiful examples of superposition of 2 emission lines. This one is in iron 11 is in red, and iron 14 is in green. And it was close to solar minimum, but there's something, so what you can see here is everything that's expanding away from the sun is at the lower temperature, and everything that's bound to the sun in these kind of arch-like structures is at the much hotter temperature. So this is one of the kind of unique findings from these eclipse observations. There's another very important feature that appeared in this particular eclipse, and this was this prominence. And I should say a few words about prominences. Well, you probably all know, but what's really unusual about them is that they are very cool and dense structures that protrude through this very hot corona, yet they seem to be isolated. They don't seem to be impacted by the fact that their shrouds are so hot. And the other thing we found from these eclipses is that all the prominences are invariably surrounded by the hottest material in the corona. So that is also telling us something about the role of the magnetic field, because the prominences are connected with very, very complex magnetic structures. And how come that this complex magnetic structures end up by forming this very hot shroud around them? So that's another puzzle. This is an example from 2017, where in these different spectral lines, we were able to capture the imprint of the passage of a coronal mass ejection through the corona. So there were 2 of them. This one happened before the eclipse, and this one was during the eclipse. And you can see that most of the coronal mass ejection, which in white light, you can't tell anything about their temperature, but in these spectral lines, you can see how the CME is at the hotter temperature, and everything that's streaming away from the sun is at the cooler temperature. This is the work done by at the time he was my PhD student, and we happened to have in 2017 3 observing sites, actually 5, but 3 of them had identical instrumentation, and the separation between them was about 1,200 kilometers. So during this eclipse time difference, so it's just not real, I mean, it's in eclipse time, he was able to show that the temperature in the corona changed its distribution changed as a function of the passage of the coronal mass ejection. So that was also a new finding. So now I'd like to turn over to some of the manifestations of the very dynamic prominences and the associated magnetic field, and what we find from eclipse observations. This is a very nice, well, I wouldn't say animation, it's a composition, a video that my colleague Drickmüller produced from the Solar Dynamic Observatory images in 3 spectral lines, the 304, which is typical of helium, 171, it's like iron 10, and 211 is like iron 14. So he chose a date when there was a flare, and this was in, I'm sorry, didn't write the date here. I think it was from 2013, and it was at solar maximum when you had lots of active regions. Yeah, it was 2011, 12. So I'll run the video. I won't run the whole thing, but I'd like you to focus on this region here, where you already see the beginning of I mean, there is a very fat prominence sitting, straddling the base of 2 active regions. So little by little, this feature is going to change in time. You can already see some flickering in the corona here. And then all of a sudden you have a flare, the eruption of the prominence, and then the material of the prominence, some of it escaping and some of it falling back. Now, because the field of view of the Solar Dynamic Observatory is limited, we don't know how much is escaping and how much is falling back. So the beauty about eclipses, again, the observations, is that, so this is from the EUV. So this is the surface as seen in the helium line, and you can see these prominences protruding above the limb, but you really have no idea of the connectivity between these prominences and the rest of coronal structures. But if you add to it the eclipse image from exactly the same day, what we saw is that we saw this also something that looked like a hook, which we now know was a projection of a very small coronal mass ejection that followed the eruption of a prominence and caused all these like wavy patterns in the corona. So it's not just the prominences associated with or triggering the coronal mass ejections, but they also triggered a lot of dynamic events, disturbances that are in the form of plasma instabilities and wave motions. So this is going back to the image I showed earlier, and this just to show you that when a prominence erupts, it stays attached to the sun. So these tethered could only be captured with eclipse observations, because if you imagine that with the EUV, you really don't see this extension here, but with the eclipse image, you're capturing everything out to several solar radii. So you can establish without a doubt that the prominences stay connected to the sun even when they erupt, or at least part of them. And this is just showing what I had just mentioned. I encircled a few features here. So what we have also from the eclipse observations established on a much finer scale how these very intricate features are connected to the arches that overlie them. So it's a very, how should I say, unique observation. It's difficult to interpret, to follow everything, but it's clear that there is a connectivity between the two. And this is the one I mentioned earlier. So then another type of observations we developed since 2015 by Adalbert Dink, who's my colleague, is he designed and developed a spectrometer that operates in high order, and it's an imaging spectrometer. So the slit, we start the observations basically at center meridian, and you allow the sun to drift, or whichever way you want to look at it. But basically the slit can scan the corona. In this case, it's going from central meridian towards the east. And in 2015, to our surprise, in the spectrometer, we found that there were bits or emission lines that are typical of prominences that showed up in the corona, Doppler shifted. So this was confirmation that from the SDO video I showed you, that these parts from prominences actually escape in the corona, and they're basically don't change their personality or their ionization state. Okay, the last thing I wanted to show is recent results from looking at all our observations, which now we have which cover more than a solar cycle. So here I have the sunspot cycle starting from 2005, and I've put the dots here where we have eclipse observations. Sometimes if we were clouded out where we could get these narrow band images in iron lines like iron 11 and 14, there were other amateur astronomers who got white light images, and they shared them with us, and Milos processed the images. So we have a very nice sequence of observations covering more than a solar cycle. So you can see here. Now, so I'm showing here the examples where we had both white light and the iron emission lines. So in 2006, we observed iron 13 instead of iron 14, but they're very close in ionization temperature. But you can see how the corona changes, not just in white light, but also in the distribution of the hot and the cool material in the corona. Now, this was a very, an important, I would say even discovery, because one thing that we found is that, again, I mentioned it earlier, but this really illustrates it from an image point of view, that all the escaping material from the corona is dominated by this iron 11 spectral line. So we wondered, well, what are we observing in interplanetary space? There are instruments that measure the different ions. So, so what we did is, okay, so let me just quickly mention that this was regardless of the phase of the solar cycle. We always found this, that iron 11 is always dominating. It's throughout the corona, and it's the one that's escaping. The iron 14 dominates all the cool, hot structures, and it's always the case regardless of the phase in the solar cycle. So this one is a little busy, but I would like to explain what it represents. So this is from a spacecraft that's observing, it has a particle detector in the ecliptic plane, and it's the ACE instrument, and it has, so it measures two things. Well, it has other measurements, but this one, we just took the velocity and we took the charge state. So this is as a function of time throughout 2006 at solar minimum, and this is in 2013 throughout solar maximum. Now, of course, we only had one observation from the eclipses, but we have them straddling solar minimum and maximum. And the iron 11 line, which corresponds to iron 10 plus, shows up as the dominant charge state in interplanetary space. And it's the dominant charge state regardless of what the speed of the wind is. So you can have fast streams and slow streams, but they are always have more or less the same charge states. Now you have some exceptions, and these are associated with coronal mass ejections, when the hot material is blown out and you have a CME. So this is just to summarize. So here we're able to follow, it's like this iron 10 plus is a fiducial link between the sources of the solar wind at the sun and all the way into interplanetary space. And because we don't have, unfortunately, any velocity measurements of the solar wind in the inner corona, we have to rely on what we observe in interplanetary space. And we see that even though this band is so steady, the speed of the wind is very variable. So this is telling us that the wind is originating not just from the polar regions of the sun, but throughout the surface of the sun. So now I just want to finish with a little more fun, is to show you some pictures from our eclipse expeditions, and just to show you it's not just a fun trip. It really carries a lot of stress and planning and so on. So what are the tools of the trade? So this is an example from 1922, which was the Einstein camera, which was several meters long, and people had to go months in advance to eclipse sites to build this structure. In our case, we have much more compact equipment. As I said earlier, if you were online, we try to all the optical systems, we carry them in backpacks or in rollers, so we don't check them. Even the spectrometer fits in a roller. Now, these are the filters here that we use for the narrowband observations. And we had, for 2017, we had tents that were custom made in China, because the sun was going to be very high and we had quite a few instrumentation. And what we do is we also use air conditioners inside the tent, not for us, but because these filters have to be kept at a fixed, well-controlled temperature. This is an example of an eclipse group from the 1901 Sumatra eclipse expeditions. And this is us, which was the largest group we ever had in 2017, because we were spread across 5 observing sites. And and we used 4 motor vehicles to get to our respective sites, and a few minivans. So throughout my career so far, these are where I have been as as a solo Wind Sherpa. So you can see that just the spread of the different eclipses, and it's actually a very fortunate thing to be involved in, because in addition to the scientific experience, there's a human side to it that it's so enriching, and you discover that the fabric of humanity is the same throughout the world and in different civilizations. So this was the 2017 eclipse across the US, and I mentioned that we had 5 observing sites. This is when the equipment we had before leaving Boulder, and this was, I showed you one of those. Now in 2019, it was a little more complicated. We planned everything, but the weather was such that, so we flew into Chile, into Santiago. And I had originally scouted the year before to identify 3 observing sites, because the eclipse started earlier over the ocean, and this was at the end of the eclipse when it hit land. So we had these 3 observing sites. And the idea was we rented motor, these campers, so that we could take our equipment across the Andes to go from Chile to Rodeo and Mascacin. And what we failed to take into account is that if it snows, the passes are closed and you can't travel. So when we arrived, the pass was closed, and they said it won't open till the day of the eclipse. So what we ended up doing is, this was the last minute. So I sent 2 teams to stayed in Chile, and the team going to Argentina, we had to fly with, I think, 20 pieces of equipment. And thanks to LATAM that allowed us all kinds of weights and sizes, we managed to make it. But it was quite a stressful endeavor. So the next eclipse is in this December 2021. I didn't think I would even think about it, because it's mostly on the ocean. In 2020, last December, we went to Chile. We had planned to go to Argentina, but because of the pandemic, we couldn't enter the country. And unfortunately, the whole of Chile was covered by clouds. So we figured, well, we can't skip more eclipses. So we're aiming for this one. Now, the chances of clear skies is very low, but we have to do it. NASA and NSF were very interested in supporting an expedition. So now the plan is to have the team split on 2 vessels. The vessels will be separated. I don't know exactly by how much, but it depends on their route. And so we're planning for the first time for an expedition on board a moving platform, such as a vessel. So you can imagine that the preparations are quite different. So I will end here, and I wanted to say that for some of the wonders of the universe, please thank the moon. Thank you.
Okay. That's wonderful, Shadia.
Do you want me to stop sharing my screen, or do people?
I think so. Let's stop sharing the screen, and if you need to go back, you need to go back.
Okay.
But the perspective on the solar corona is truly impressive, and I think you've made your case that you really need these eclipse observations to connect what's going on near the surface of the sun to what's going on in the outer corona, which is the part that ends up impacting us. Also, I just think those multiple emission line images and the way you've combined them is very artistic. So I actually have a question.
Yes.
So I noticed that you have found that the polar streamers, the streamers coming out of the poles, have a lower electron temperature,
Yeah.
and because they have a stronger emission in that iron 11 line. And isn't that where the wind speeds are the highest?
No, this is the interesting thing. That's the what people, that's the current thinking, but this is what I wanted to. So if I can, I'll share this one.
And go back.
Sorry. Okay. So here I wanted to note that the ACE spacecraft is in the ecliptic plane. So it is not measuring wind coming from the poles.
Okay.
And yet to see the speeds going from 300 to 700. Now, and all the time. Now, the first detection of the solar wind was also the same. It was in the ecliptic plane. Now, people developed all kinds of theoretical models and so on, and they found some ways to convince themselves that all the wind, the fast wind, came from the polar regions and just went down to the ecliptic by the way the curvature of the streamers, the boundaries of the coronal. I have been following this idea for over 20 years to try to prove it wrong. And this is, at the end, I was able to with these observations over such a long period of time. Because you can clearly see that the charge state doesn't change, with a few exceptions. And you have these streams of particles that have different speeds, and yet the fact that they have the same composition. So it's coming from the same source at the sun. And when you look at the eclipse observations, you can see that the iron 11 isn't just in the poles, but it's all over. It's whatever keeps on expanding past the closed arches.
Okay. So I guess that also says that the sun is more dynamic. It's not in any sort of energy equipartition. I was thinking that the maybe at the poles, if the speeds were higher, the temperatures would be lower, so there'd be kind of like an equilibration of the total energy. But apparently the sun is definitely out of equilibrium wherever you look.
Yes. But what's really curious is that this finding is telling us there is something at the sun that's controlling the temperature at the source of the solar wind so that it does not exceed the ionization temperature of iron 11, what I called iron 11. And this is the ion that makes it all the way to interplanetary space. So you see the higher charge states occasionally because they're coming from, when you break up, you open up these closed arches through the coronal mass ejections, then you're spewing these hotter ions into the solar wind and you detect them. But on a, let's say, standard, the continual solar wind is all this, just this, it's dominated by this lower charge state of iron That's telling us something about processes at the sun that are kind of keeping this temperature kind of controlled over a certain value, by a certain value.
Okay. So I should hush up for a bit. Does anybody else have any questions? Feel free to unmute.
Excuse me, would there be any hope of seeing anything during an annular eclipse?
I'm sorry, I didn't understand what you said. Could you repeat your question?
During an annular eclipse, I mean,
Yes.
I suppose the sun has to be totally obscured, but if when it is just covering one of the edges, when it slides over, is it possible to see any prominences or anything like that during an annular eclipse, do you think?
Oh, you could see, well, I have to think. It's very difficult. If you see any prominence by luck, you won't see the corona. Because they, even for example, when you're observing a total solar eclipse, its progression, the coronal features don't appear until what people see the diamond ring effect, which is the sunlight coming through, one of the valleys on the moon. And then you don't, but before that, you don't see the corona.
Okay, thank you.
Except I should add with the spectrometer, it just so happened, and we could, then when the slit was on the side of the sun, which was already obscured, Professor Ding was able to see some coronal emission, but it was really a very, very short period of time, like seconds, yeah.
Michael?
Okay.
What?
Yeah.
Okay, yeah, I don't have the background to ask an intelligent question. I just wanted to add my voice to Bill's, compliment those multicolored temperature maps. A great way to present the data.
Oh, thank you. Thank you.
Tom?
Yeah, I had a question. During the observation of the coronal structures during the total eclipse, is there a way to resolve if any of the velocity components of those structures is toward or away from the Earth? Because some of them could be coming from the surface that's not at the edge that we see. It could be coming from something that's behind the moon or behind the sun and then coming radially outward and have a component that makes it more three-dimensional. Is there a way to capture those velocities?
Yes. So for example, with the spectrometer, when we have the slit starting, it intercepts the occulting moon, but part of the slit goes over the poles. And let me just to answer your question, I'll show this one if I may share my screen.
While you're doing it, there is a spacecraft called Stereo, which is actually two spacecrafts which are separated in orbits around the sun. And in that way, they've been able to kind of get some of the three-dimensional information.
Yes, that's correct. But I'm saying with an eclipse, I think your question, I don't know, Tom, were you asking just about eclipses or? So for example, in this case, when we started the observations, imagine I didn't draw a slit, but the slit goes north-south. And it intercepts the blocked moon, but then it also looks at the corona. So if you have any motions here along the line of sight, away from the observer or towards, you will see a Doppler shift in the spectral lines you're observing.
Oh, okay.
So, and this is how we actually trace these sections or parcels, is through the Doppler shift. So all these were redshifted when we took the observations 2015. So all this material was going away from the observer. But this was associated most likely with a coronal mass ejection because the speeds were very, very high.
I was just thinking, if you see a structure that looks like a loop inside a loop, it may be that one is behind the other.
Yes.
They're not really super close.
Yes.
Okay.
Exactly, because here yes, I mean, you're looking through lots of plasma. So,
Right.
and you can see it's almost like well, it is transparent and it's optically thin. So you do see this superposition in these white light images, which is really incredible, because it's not just features in this plane, but it captures features out, closer to you and away from you.
Oh, good. Thank you.
You're welcome.
All right.
May I make one minor comment?
Paul,
Yes.
go ahead.
This is Paul Maley. There was a question asked about observing prominences during an annular eclipse, and the answer is yes, it is possible to do that and to photograph them, but it all depends upon where the prominence is located and the degree of annularity. You might have an annular eclipse that has maybe 10% of the sun showing. You might have an annular eclipse where 1% of the sun is showing, where you have much greater contrast along the edges of the sun where prominences can be seen. So it is a serendipitous situation where you must be in the right position to be able to distinguish the prominence during a particular period of time in the sequence.
Yeah, thank you, Paul.
Thank you also.
And I should note that there is a total solar eclipse that's going to go through the United States of America in 2024 in April. I don't remember the exact date.
Eighth.
April
8th. All right, thanks. And it goes from Mexico through Texas and onwards to Maine. Is that correct?
And past it to Canada. Yeah,
Past it,
northern
yeah.
Canada. Yeah. So we will hopefully, I mean, be having several observing sites. That's the plan. But I can't plan that one when I'm doing 2021.
No, not when you're doing Antarctica, for heaven's sakes.
Yes, I have to wait a little. It's just the logistics. When we used to do just one observing sites, it was much easier. But now with several observing sites and we're doing it for many reasons. One is to maximize our chances of getting observations. And second, because you can actually see the changes in the corona and capture dynamic events.
Right.
So we'll try to do that. And everybody thought I'm crazy, well, for 2021 to try to do two vessels, but I'm doing it.
Well, maybe you are.
Yes, I am crazy. I know.
So, but I encourage people here living in the States to see if they can get to the center line, or, to that path of totality, which is 100 miles wide, somewhere along the path.
Yes.
Is it a 2,000-mile path? And caution that the weather probably will be better in Mexico and Texas than in Maine.
Mm-hmm. Well, you never know. I mean, in Svalbard in 2015, we had a 50-50 chance of clear skies, and we had gorgeous clear skies. So yeah, it's hard to predict. I mean, you have the statistics and so on. Sometimes you have 99%, statistically speaking, clear skies, and you get the 1% and a cloud that comes right in front of the sun that forms right before totality and disperse right after. And it has happened several times. It's heartbreaking, but it happens.
It happens. We
So,
are
yeah.
Somebody always wins the lottery, keeps you coming back.
Yeah. We are victims of the air we breathe. So,
Yes. Uh-huh.
well, this has been wonderful, and I'm so glad that we were able to get you, Shadia, to
Oh, thank you.
represent the sun and its dynamic atmosphere in such beautiful ways. So,
Thank you very much. Thank you for inviting me.
okay, so on that note, I'm going to end the recording and bid you all adieu.
Okay. Bye-bye.
Bye.
Thank
Bye.
you so much.
Bye. Bye. Thank you.